Good day. This video will be on chapter 5.4, the mean value theorem. So a good place to start would be the mean value theorem for functions of one variable. Now remember in first year we had the following definition. If f is a function on a closed interval from a, b to r and it's integrable, we define the average value of function f on the interval from a to b as follows. It is the integral from a to b, and then we divide it by b minus a. So we're going to start off and asking, can we also define the average value of a function in 2D? So for example, if you have a region and you know what the function values are at all points on the region, can you find the average value of the function on that region? And obviously the answer is yes. Now, to do the definition of f average, we're going to need a new idea. And this is what's capsulated in the definition. So let D be a bounded subset of R2. We define the area of D as follows. So the area of region D is defined as the double integral of 1 dA over region D. So we just make the integrand 1 if the integral exists. Alright, and now we can define the concept of an average value of a function on domain D. So we say if f is a map from set D to R and it is integrable, we define the average value of f on D as follows. F average is equal to 1 over the area of D times double integral of f over D. So remark, so to do this calculation, you need two double integrals to do this. You need one double integral to work out the area, and then you need a double integral to work out f average. So do practice this, and there's some nice examples in exercise 5.4 to do. But please notice the similarity. So in 1D, we define f average as 1 over the length of the interval, and we integrate over the interval of f dx. And in 2D, f average is defined as 1 over the area of D, the double integral of f over D. So the single integral gets replaced with a double integral, and the length of the interval gets replaced by the area of region D. So very similar formulae. All right, Now we know that the mean value theorem for functions of one variable was stated as follows in year 1. If f is a continuous function on closed interval a to b, then there exists a real number p in the closed interval from a to b such that fp equals f average, which we just stated for a function of one variable. F average is the integral from a to b divided by the length of the interval. Now we want to ask, can we also have a mean value theorem for a function of two variables? And as before, the answer is yes, but we need a new concept. So to be able to do this, remember if you're in 2D, you can't talk about a closed interval. So you got to talk about subsets which are special. So we know we can talk about closed subsets, we know we can talk about bounded subsets, but we also need a new concept. And the concept we're going to need is the idea of path connected. So here is the definition for us. A subset of R2 is path connected if for every 2 points P and Q in D, there exists a continuous vector valued function, which we label R, from the unit interval from 0 to 1 to D, such that R0 is at P and R1 equals Q. It's a bit better to understand this with diagram. So if you look at figure 1, figure 1 is a path connected subset of R2. So here you can see you have a vector value function that at time 0, you're at point P. At time maybe a half, you are visiting some point in region D, and at time 1, you're at point Q. So the one on the left is a path connected set. So you can see that any 2 points that you pick, you can find a path from the first point to the second point that's completely inside the region. All right. And sometimes you can see what they've done here. They scaled it up so that at time 0, you're at point P, and at time 1, you're at point Q. And you can see it's a vectored valued function because for every time from 0 to 1 inclusive, the output is a 2D vector, which is a point in set D. So it's a 2D vector. So it's all those red points. But now if you look at figure 2, if you pick point P, which is in the blue region, and if you pick point Q, which is in the blue region, it's impossible to find a path from point P to point Q that's completely inside set D, a continuous path that's completely inside set D. So what we say, if this happens, then the set is not path connected. So here you have two diagrams. The one on the left was path connected, and the one on the right is not path connected. So the remark says, visually, you can travel between any 2 points by having a path inside region D if it is path connected. So if it's path connected, we say it's a connected set. So figure 1 is a connected set, and figure 2 is a disconnected set. All right. And now, armed with this new concept, we can now define the mean value theorem for function of two variables. And it goes as follows. Let D be a closed and bounded and path connected subset of R2 with positive area AD. And F is a map from D to R, which is a continuous function. Then there is a special point P in set D such that if you evaluate F at that point, it is F average, which we defined as 1 over the area of D times the double integral of F over D. So the mean value theorem says that under the correct conditions, there is a point in the domain D where if you evaluate F at that point, it is equal to F average. I want to emphasize, so for the mean value theorem for functions of two variables or even higher dimensions, we need this idea of path connected. So theorem 151 only applies if D is path connected. Now the good news is you may skip the proof of this theorem unless you're going to do third year mathematics. In that case, I strongly suggest you read the proof on page 140 to make yourself stronger for third year. The proof is very nice, and somewhere in the proof they also use the idea of the intermediate value theorem, which you learned in first year, and you will revisit the intermediate value theorem in second semester. So do remind yourself, what does the intermediate value theorem says? All right, it's needed in this proof, and you will see it again in WTW 220. All right, now we haven't done any problems. So let's finish this short lesson by doing an actual problem. So the problem goes as follows. Let D be the region bounded by y equal to x squared and x equal to y squared in R squared. And we want to find all points P and D such that F at those points equal to F average, which is 1 over the area times the double integral of F over D. And F is a function of two variables, and here we have F is a function square root of x squared. All right. Now, we want to use the mean value theorem for a function of two variables. So we first need to know, what does region D look like? So let's start there. So let's look at region D. So we want to know when y equal to x squared, and that's got to be greater or equal to 0, and x equal to y squared, that's greater or equal to 0, intersect. And so we see the following, that x is equal to y squared, y is x squared squared, that's equal to x to the power 4. And so we now have to solve when is x minus x to the power 4 equal to 0. So we get x times 1 minus x cubed equal to 0. So x is equal to 0 or x is equal to 1. And so now, next we're going to do is we're going to draw this region. So if we draw the two regions, remember this is a subset of R2. So if we draw the region, we worked out that they intersect at the origin, which is the point 0, 0, and at the point 1, 1. And so we draw the curve y equal to x squared and x equal to y squared, and it looks like this little leaf. So if you draw it, it looks like this. I'm going to leave it for you to verify. The one at the top is y equal to the square root of x, and the one at the bottom is y equal to x squared. So this is region D. And now we can say D is closed and bounded and path connected, and F, which is the square root of x, is continuous on D. So by theorem 151, such P element of D exists. So by the mean value theorem of a function of two variables, we know that there are points in D where f of those points will equal to the average value. All right. Now, to find those points P, we first need to work out f average. And to first work out f average, we first need to work out what is the area of D. So let's start with area of D. So the area of D, we're going to write this as a double integral over D. The integrand is 1 dA. Now I'm going to treat this as an iterated integral, and I'm going to make vertical slices. So if I make vertical slices, you can see my x value starts at 0 and my x value ends at 1. So by making vertical slices, I know this is a double integral. X is starting from 0, ending at 1, and the integrand is 1. And now we've got to say, where does y start? Y starts at x squared. Where does y end? It ends at root x. So I have correctly turned this double integral into an iterated integral of the form integral from 0 to 1, integral from x squared to root x, 1 dy dx. And now I just quickly do this calculation. If I integrate 1 with respect to y, that's y. The top bound is root x, the bottom bound is x squared dx. And if I plug in, I get root x minus x squared dx. And then I integrate x to the half. If I integrate x to the half, that'll be 2/3 x to the power 3 over 2 minus x3 over 3. Plug in 1 and 0, and then I see that the area evaluates to 1/3. And now the next calculation we're going to do, we're going to work out f average. So before we work out f average, let's quickly do the double integral over D of the function dA. So the region didn't change, so we know it's an integral from, we can write this as an iterated integral from 0 to 1, the integral from x squared to root x. The function is root x. So the function that we want to find its average is a function root x, and then the order is dy dx. All right. So now we got to do this calculation. When we integrate root x with respect to y, then it becomes y root x. The top bound is root x, the bottom bound is x squared dx. And now when we replace y with that, root x times root x becomes x, and this becomes x to the power 2.5 dx. And now this is an easy first year problem. So if I integrate x, that becomes x squared over 2, and that becomes x 3.5 over 3.5. Plug in 1 and 0. Going to leave it for you to verify that this works out to be 3 over 14. So if you do this calculation, you get 3 over 14. And so now we can say f average. The formula for f average is 1 over the area of the region, double integral of the function f over region D, dA. And so we've worked out this integral is 3 over 14. And if we divide it by the area, which is 1 over 3, then this works out to be 9 over 14. All right. Now we want to find all P. So we want to find all the points P in domain D such that FP equal to the average. So we want to find all the 2D vectors so that in domain D or region D, so that if we plug it into F, that will equal to 9 over 14. And we know that F at the point xy works out to be root x, which is 9 over 14. So we see that x has got to be 81 over 14 squared, which is 196. Now remember, our region was a little leaf. So let me quickly redraw the region that we had. So our region was a little leaf like this. The bottom curve is y is equal to x squared, and the top curve is y is equal to the square root of x. And we see that we are looking for all the 2D vectors when x equal to 81 over 196. So we can say that there are infinitely many points in D with this property, and they are in set notation. It's called set S, the answer set. It's all of the vectors of the form 81, 196, comma y, where y is between 81196 and 9 over 14. So you see, it is all of these green points. So all of these green points, if you evaluate f at all of those green points, it will equal to 9 over 14, which is the f average of this function on region D. So to describe all of the green points, I'm going to say it's all of the 2D vectors of the form 81, 196, y, where the y value is between x squared and the square root of x. So because it's x squared, this should actually be that value squared. So x is 81 over 196. So y lies between x squared and the square root of x. So y lies between this value and this value. I hope you enjoyed this example and you enjoyed this video. Till next time, good day.